I was going to show you one more data set in the survival analysis material that we'll finish up with here today. And then if we have time, I'll start on missing data material. So I'm downloading a data set called UIS-Serve and the script that goes with it. What I'm going to use these data to illustrate is how to handle a time-dependent covariate with a Cox model. So let me briefly review the issue. What is a time-dependent covariate? And how can we deal with one? And then I'll show you with a real example. Okay, so there's a handful of kind of technical issues that come up with Cox models, one of which was time-dependent covariates. Something like, have you ever smoked before? Could be something that we record at the beginning of a study for somebody, and then it does not, we assume that it does not change over the course of the study. So a fixed quantity at baseline for the study is one way to define covariates. But there may be cases where the covariate you're interested in can change over the course of the study. Have you ever had a cardiovascular event, for example? At baseline, maybe the answer is no, but 6 months into the study, maybe the answer becomes yes. So a Cox model can handle a time-dependent covariate, and it's fairly easy to do it. So I lectured through these slides last time, which is somewhat helpful to see the math, I guess, but maybe more helpful to see actual example. So let's go look at this UIS-Serve data set. I'm going to open up the script, and there is a time-dependent covariate in this data set that we will deal with. Okay, so these are survival data for people with AIDS. Five-year randomized trial of so investigating or assessing the effect of a residential treatment for drug abuse. So I guess these are not AIDS patients. These are people who are at risk, high risk for HIV contraction. If you're a drug addict, and in particular if you're using something like heroin where you're shooting with a needle, that's high risk for contracting HIV. So for people who are involved in drug abuse and high HIV risk behavior, this study proposed a quote, residential treatment protocol. All they mean by that is a long-term treatment routine, as opposed to, here's a pamphlet, good luck, or a couple of nights at a treatment facility. This is referring to a long-term, like weeks on end, kind of can't think of the word, intensive treatment. in particular, there were 2 treatments that were considered in this study, and they differ by the length of them. So treatment, one of our variables is treat. It's the randomization assignment type of treatment, and it's either short or long. I don't know what the details are, but like stay for a couple of weeks, or do you stay for 6 weeks? Okay. And okay, so one of the challenges with this data set, we have people who are potentially drug addicts, and they're coming in to be a part of this trial, and the treatment from the trial is a long-term commitment. So people who came into the trial, in some cases, dropped out of the trial. So you're randomized to the long-term treatment, say. You're supposed to be here for 6 weeks. You stayed around for 2 weeks, and then you went away. So that's an issue with these data. Not everybody completed the treatment regimen. The event time, these are survival data, time to event data. The time to event is the time to relapse on the drug usage. These are all people who have been using drugs. They are being treated with either a short-term or a long-term intervention. And what we're interested in is how long until relapse. So it's not survival in this case, but it's relapse. And we would be interested in, is the survival prognosis, or the quote, survival prognosis better? Do you tend to last longer on the long treatment versus the short treatment? Is there a treatment effect in terms of time to relapse? So we could think of a regression model, a survival model that says event time together with the censoring indicator. A censored observation in this context, by the way, is a little different from the cases where we've actually been talking about death. So an uncensored observation, an actual event, is somebody who returned to drugs or dropped out of the study altogether, which is a little bit unusual of a parameterization. But we're defining the censoring indicator as 1 if relapsed or dropped out of the study altogether, and 0 as some other, so 0 would be end of the study. They're still in the study and they have not yet relapsed. We're interested in time to relapse. So each person, we either observe them until they actually relapsed. Okay, this person lasted 155 days and then they went back to drugs. Or they are lost to our study. They drop out of the study, in which case we know that they lasted 155 days because that's the last time we saw them. But other than that, we won't know when their actual relapse time is. Or the third possibility is the person lasts through the entire treatment regimen, so their whole 6-week treatment, they saw it all the way through, and we never observed them go back to drugs. So the way this study parameterized the censoring was if you made it through the entire study without relapse, then we're going to call you censored, because we don't know what time you relapsed. This bothers me a little bit, the loss to follow-up. It doesn't seem like we should be including that in this category. So definitely calling an individual who was observed to relapse at a particular time as an event. That makes sense to me because we're specifically interested in time to relapse. I don't have much to defend this being lumped into that category. So I need to double check to make sure I got this right, but this came right out of our book, so I think it is right. So for our purposes, let's think of it as we're doing survival data. It's not really survival though, it's more time to event. And the interest specifically is time to relapse. And we want to do, say, regression with these time to event data. We've been using the Cox proportional hazards model. So we could say Cox model, time, tilde, and then we have these covariates that we can draw from. The treatment group, certainly, we're interested in that. Race, number of prior drug treatments, history of IV drug use at admission, heroin and cocaine use during the last 3 months leading up to admission. We have a quantification of depression. We have age. Okay, let's read in the data and have a peek. We have 628 individuals. Here are the first few rows. ID variable tells us a unique identifier. Age is age in years. Depression, heroin, cocaine. So those numbers, this is a categorical variable, and it tells us in the 3 months prior to admission, if you used heroin and cocaine, this is coded as 1. If you used only heroin, it's coded 2. Cocaine only, it's 3. And neither is 4. Similarly, the IVHX, IV history variable, is categorical. Okay, let's look at a summary of the data, just to get a feel for any outliers, are there missing values, that kind of thing. So there are some missing values. Age has a few, depression has more, heroin, cocaine, IV history, number of drug treatments, and race all have some missing values. Something like heroin, cocaine, or IV history, you're asking every study participant, tell me what your history has been with respect to heroin and cocaine over the last 3 months. That's the kind of sensitive question that you wouldn't be surprised to see people leave blank. I don't want to answer that question. So not surprising that there are some missing values there. Okay. All right, so here's the deal with these data. We have, in addition to the time variable, time to relapse, we also have length of stay, LOS. That's not our event time variable. That is how long did you comply with the treatment regimen. You were scheduled to be here for X number of days. That's the duration of the short or long treatment. We have recorded, though, for every person just how long they did stay. And so what we're going to do is create a new covariate called OffTreat. We're going to create a new covariate called OffTreat that will be 0 if you're complying with the treatment routine, and 1 if you are not. So if you drop out of the treatment program and you're not coming as you're expected to, you're going to have this covariate OffTreat that turns on. Each individual then has the potential to have this variable equal to 0 for part of their time in the study, and then equal to 1 for other part of the study, the latter part of the study. It's a time-dependent covariate because it can be one value at the beginning and then change values towards the end. And in order to incorporate this, it takes a little bit of work in R. So let me show you what I'm doing in this chunk of code here. I'm going to build a new data frame that represents, that contains this new off-treatment covariate, and that represents, the individual before going off treatment and individual after going off treatment, in such a way that Cox PH will be able to recognize that we have a time-dependent covariate. Because if you think about it, if we just have a data set with event times and censoring indicators delta, and then we have these covariates x, so let's say yi, delta I, and a covariate vector xi. If we're going to fit a regression model, then all we know to do in the context of Cox models, for example, is log hazard at time t given covariates equals beta 1 times x1i plus beta 2 times x2i plus ... And every one of those x's, all we know to do is put a single number in there, or a single category if it's a categorical variable. So what if one of these covariates, like this one, what if this is what we're trying to make off treatment? We don't have a way that we know of yet to let that be 0 some of the time and 1 other times. Here's how you can do it. Let me run this and show you what results, and then we can talk through the code and where it came from. So remember, this is what our data looks like, the raw form. We have a single row for every individual. Row 1 is for ID number 1, that's individual 1, and we have all their covariates. There's no off-treatment variable in there because we haven't created that yet. But let's look at this individual 1 for a second. This is a 39-year-old, guess we don't have gender, that's weird. 39-year-old person with a 9 on the depression score, has not used heroin or cocaine in the last 3 months. I forgot what that is. IV history means recent IV drug history use or drug use. Number of previous drug treatments, 1. Race category 0. In the long-term treatment group. And we have length of stay equal to 123. That means they were in the treatment routine for 123 days from baseline. But the event time until relapse, was 188. So that means this person was under observation for the first 123 days, but then was not under observation anymore, or at least not in the treatment routine anymore for 65 days, after which they were observed to relapse. And similar things are happening for many of these individuals. Here's another one who was in the long-term treatment routine. They were in the treatment for 25 days, and then they dropped out, and the very next day they relapsed. There's another person who only lasted 7 days in the treatment routine and relapsed after 207. So that's our original data, and now we're going to slightly modify it to make it look like this. So now, notice that there are 2 rows for each of the individuals. ID 1 is in rows 1 and 2, both of them. Most of the covariates are exactly the same because these are baseline measures that are not time dependent. But what is time dependent is the new variable off treatment. So in the first case, it's 0 for individual 1 because beginning at time 0 and ending at time 123, they were in the treatment regimen. After time 123, remember, they dropped out of the treatment. So my second bit of information for this same individual covers this time period from 123 to 188, during which they are off treatment. Let me show a few more of these rows. So let's look at the first 25, say. Most of them follow a similar pattern to what we just said. Somebody was on treatment for the first so many days, then they went off, and we observed them until relapse or end of study. Most of them look like that. Here's one that's a little bit different. Let me look at these right here. Individual 5. Individual 5. Was under study for 173 days. Is that right? Didn't get it right. Here we go. Like that. Yeah, individual 5 was participating in the treatment for 173 days, then stopped participating, so OffTreat turned on. And our last observation of this individual was 551 days, but the censoring indicator is 0. Everybody else before this individual 5, had some time under study or some time under the treatment, and then some time where they're off treatment, and then relapse. Censoring variable equals 1, actual relapse. For this person, same story, except at the end of this, after 551 days, apparently maybe the study was done. They're out of our hands now. We will not be able to observe when they actually relapse. But for most people, we just have this 2 rows for each ID and a time-dependent covariate. And it turns out you can just pass the data like that to Cox-PH, which is a little bit surprising because we have multiple entries for the same person. I have 2 rows in my data set for each ID. So you might be concerned about correlation between the individuals, and maybe is the Cox model handling correlation correctly? So it turns out that it doesn't have to worry about the correlation because of the way it estimates the model. Cox-PH is able to handle data set up like this. And here's the kind of thing we get out. So I fit Cox model. Notice that the syntax is a little bit different. We're doing, instead of capital serve object with event time, comma, censoring indicator, now we're doing capital serve object with a starting time and a stopping time and the censoring indicator. So we're providing an interval of observation. each individual has multiple intervals of observation and distinctive censoring indicators. So it's typically sensor equals 0 for the initial observation, and then either 0 or 1 for the latter observation. But it's going to take those start and stops that we created. This was part of the code that I ran a moment ago, was to take the original data, which was just event times, and turn them into start and stop times and corresponding censoring indicators. So we can pass our data in like this and use this time-dependent covariate. And the output looks a lot like what we're used to. Summary fit. So when I passed this in, I did treat times OffTreat. Treatment is 1 or 2, or 0 or 1 for short or long term, and then OffTreat is 0 or 1 for yes or no, are you off treatment. So if you say treat times OffTreat, you get treat and OffTreat and the interaction. That's shortcut syntax to say, give me the main effects and the interaction. So here's a usual Cox model output. No intercept. Remember, we don't have an intercept with a Cox model. But I have a treatment effect, and I have this off-treatment effect, and an interaction. So I could interpret things interestingly, like what is the effect in terms of risk of going off treatment? We're modeling log hazard. That's what we do with a Cox model. And the log hazard ratio corresponding to going off treatment, dropping out of the routine, is 2.28. That corresponds to a hazard ratio of almost 10, which is extremely statistically significant. So we were able to turn the issue of people dropping out of the treatment routine into a covariate. And we can see quantitatively that dropping out of the study is a bad move. If you're trying to stay off the drugs, don't drop out of it. We also have, interestingly, that there's a statistically significant interaction between treatment group and off treatment. In particular, so let me just write down this model real quick so we're clear on what we are saying. Our model is log hazard at time t given covariates equals beta 1 times treat plus beta 2 times off treat plus beta 3 times the interaction. So, for somebody who is currently in the treatment program, off treatment is 0. So if off treatment is 0, the only thing that's in the model is beta 1 times treat. That means that beta 1 is a log hazard ratio comparing treat equal 1 to treat equals 0. This is the log hazard ratio comparing long treatment to short treatment. Among those currently under treatment. Because beta 1 is the coefficient for treatment only if off treatment is 0. By putting in an interaction, we're allowing for there to be a long to short effect that depends on whether or not you're currently under treatment. Beta 1 is the log hazard ratio comparing long to short among those for whom off treatment equals 0. Beta 2 is the log hazard ratio comparing, let's call them dropouts, to those currently in treatment. And here again, because of the interaction, I have to specify that this is among those in the short treatment group. So beta 2 is the effect of off treatment only if treatment is 0 because of the interaction. Beta 3 then is an interaction effect. So interactions we interpret like differences of differences. In this case, the differences are log hazard ratios. So beta 3 would be a difference of log hazard ratios. So I could write it like it's the log hazard ratio comparing long to short treatment among those for whom off treatment is 1 minus the log hazard ratio comparing long to short treatment among those for whom off treatment is 0. That stuff that I just wrote down on the screen is analogous to what we've done before with interpreting regression coefficients. So when we've seen a few times models that have interactions in them, and I'm just reproducing what we've said before is the way we interpret them. So with this model, we can estimate 4 different hazard ratios. There's hazard ratio of treatment effect for those who are currently under treatment. There's hazard ratio of treatment effect for those who are not under treatment anymore. There's hazard ratio for going off treatment for those who are in the short treatment regimen. And there's a hazard ratio for going off treatment for those who are in the long regimen. And we can look at each one of those by manipulating the coefficient estimates. I'll show you a couple of them. For example, among the folks who are still under treatment, for whom off-treat equals 0, what is the estimated log hazard ratio? Or we could ask for estimated hazard ratio if we exponentiated stuff, comparing the long to the short. Among those who are still under treatment, what is that hazard ratio? The first of our 4 corresponds to beta 1. Like I said on the whiteboard, beta 1 is the log hazard ratio comparing long to short among those for whom off-treat is 0. So here I'm going to get the coefficient estimates from the model, beta hats, beta 1 hat, beta 2 hat, beta 3 hat. so let me look at what that looks like. CF. This is the table of coefficient estimates from the Cox model. So remember the coefficients themselves are log hazard ratios, which means if you exponentiate them, you get a hazard ratio. Like this right here. If I say e to the first row, first column of the coefficient matrix, I get that hazard ratio, 0.59. And then if I wanted a confidence interval, say, for the hazard ratio, my estimated hazard ratio comparing long to short among those who are still under treatment is 0.59. That's less than 1, which indicates that the longer treatment regimen is better for you or protective. The longer treatment regimen has a lower hazard than the shorter treatment regimen, at least among people who are current in their treatment. And that's statistically significant, 0.02. So suppose we wanted a confidence interval for this hazard ratio. What we can do is construct a hazard ratio for the construct a confidence interval for the log hazard ratio. So we could do that coefficient plus or minus 1.96, say, times the standard error of the beta coefficient. That would be a confidence interval for log hazard ratio. And it turns out if you want a confidence interval for hazard ratio, you can just exponentiate the endpoints of the confidence interval. So that's what I'm doing right here. Exponentiate beta 1 hat plus or minus 1.96 times the standard error of beta 1 hat. The p-value was less than 0.05, so if I compute a 95% confidence interval for the hazard ratio, I expect that it will not contain 1. There's a duality between confidence intervals and p-values. If the p-value is smaller than 0.05, a 95% confidence interval won't contain the null value, and vice versa. So here we had a small p-value. My confidence interval, as expected, does not contain 1. The longer treatment regimen is protective. It's better. It seems to be statistically significantly better in terms of extending time until relapse. Okay, we don't need to go through all the rest of these, but this is, I told you there were 4 hazard ratios that we could look at. There's the hazard ratio for long to short among those currently on treatment. There's a hazard ratio for long to short among those who are off treatment. Might as well look at that real quick. I'll just look at the second one and then we'll leave the rest of them for self-study if you're interested. Let's compare hazard for treatment equal 1 to treatment equal 0. That's long to short, but now among those who are off treatment. So off treat equal 1. We didn't write it out here, but off treatment equal to 1 would turn on the beta 2 coefficient here. So beta 1 plus beta 2 is the log hazard ratio, not beta, yeah, it should be beta 2. Should be beta 1 plus beta 2 plus beta 3. should be the sum of all three, is the log hazard ratio comparing long to short treatment among those for whom off treatment equals 1. So they have dropped out. So if I wanted a confidence interval, say, for a hazard ratio comparing long to short among those who have dropped out, I could look at beta 1 plus beta 2 plus beta 3, get an interval for that, and exponentiate that. But in the output, we do see this statistically significant interaction term. So we do have evidence that dropping out of treatment is detrimental. It increases your risk of relapse. Yeah. So I'll leave it at that for our survival data. Remember how to spot survival data, censoring. It may not be presented to you, your data, as censored data. So it may be up to you as the analyst to decide and ask the right questions. Tell me about the nature of these data because I want to figure out if there is censoring. If there is censoring, you need to deal with it. Just like if there's correlation, you need to deal with it. Okay. So let me just very briefly introduce us to the idea of missing data, and we'll pick up on that Monday. So let me get the notes for missing data just briefly here and say a couple of things about it. Missing data is one of those things that shows up an awful lot in practice. A lot of data sets have one or more missing values. The one we were just playing with had missing values. And if you try to do statistics with data with missing values, there can be problems. You can't compute, for example, a standard deviation of a variable for which there are some missing values. You have to make a decision about what to do with the missing values. If you just say SD of some numbers, 1 for NA0, R will punt, it'll give up because it doesn't know what to do with the NA. There are ways around it. You can say, for example, in many of the R functions, you can say NA.remove equals true, for example, in which case you're saying just ignore the missing values for the purposes of the calculation. But if you're doing regression and you have response variable and several covariates maybe, you might have a missing response for one individual. You might have a missing covariate or two for another individual. This that we just did with this really simple case, ignore the missing values please, is essentially like throw out any individual that's not complete. Throw them away. Don't use them in the calculation. If you're doing regression, like with our UIS serve data, there's missing values that are spread out among different individuals. Some of these individuals might have multiple missing values, but there's going to be some individuals that have one missing value for this variable and other individuals that have missing values for that variable and so on. So it's more complicated to decide what to do with the missing values. You don't want to just as a blanket strategy throw away every individual that has missing data because you will end up with not a very big data set in many cases. You'll lose a lot of data, a lot of information. If, for example, we have an individual in this data set for whom we have event time and censoring indicator and everything except depression score, We have a lot of information on that person. We just happen to be missing one variable. So R can generally handle NAs with a regression context. Like when we did our regression here, we didn't say anything about missing values. We passed in data that had missing values. But R was able to handle it. It did something with those missing values. So what you do with the missing values depends a lot on why the values are missing in the first place. So let me just briefly introduce you to that issue, and I'll let you go for the weekend. So this is the missing data script, or notes, and let me come down to here. So let's think about data that for each individual, let's say that for each individual we observe them at specific time points. We observe them over time, maybe once a month. For each individual and each time point, you tell me the individual I and the time point t. For each individual, we have data at I or at time points t. So suppose that individual I time point t is missing for some reason. This is a clinical trial. We're measuring pain. You come in every month and we measure the pain. You skipped last month. So I have your first 6 months. I don't have last month, but I see you this month again. So your data consists of some numbers, but there's an NA in there. What we're going to need to think about is what was the mechanism that gave rise to the missingness? Why is your data missing? Did you fall down the stairs and break your leg and it was completely an accident and you just were not able to come in? That's one possibility. The fact that your data are missing was like a random act. Had nothing to do with the study, nothing to do with your illness with respect to the study or the drug or any side effects or anything like that. There's a type of missingness called missing completely at random, MCAR. And the idea is that the probability that you are missing an observation at IT is independent of your response and your covariance. In particular, the probability that an observation goes missing under MCAR does not depend on what the response would have been at that time. It does not depend on what the response was at any other times. And it does not depend on your covariance. So it's completely random. Like you fell down the stairs, it had nothing at all to do with the study. That's the best case scenario for missing data. When things are missing completely at random, we can essentially ignore the missing data and not bias our results. Another possibility, I'll just show 3 of them, we're out of time, is missing at random, which means that the probability of missing only depends on the data that we observed. So if the fact that you are missing, if you're more likely to be missing, or if I can explain the missingness in terms of the data that I did observe, that's something we can also deal with. It's not as easy to deal with as the missing completely at random, but things like imputation, if you've heard of multiple imputation techniques, those are applicable to missing at random. The hardest, most pathological case is called missing not at random, and this is when the probability of missingness depends potentially on the value we would have observed. So for example, in a clinical trial, if you are more likely to drop out the sicker you are, that's missing not at random. The probability you are missing, that you drop out, depends on what your response would have been. For people who would have had worse responses, if they're more likely to drop out, then there's a problem. And this is much harder to deal with in practice. So, we'll talk about it. Yeah, well, I'll just leave it at that. We'll talk about it starting on Monday. Next Wednesday we don't have class. It's a reading day. And of course Friday's a holiday, so we'll just see each other on Monday. And then the next week is the final week of lectures. And you'll get your take-home exam the Friday of that week. Okay? Have a good weekend.